Up until now, we've always used an array when we want to have a sequence of data items. So we allocate an array and we step through the array when we want to visit each item. But an array has some limitations. One is that it's a statically sized, or it's a fixed size sequence. When we statically allocate an array variable, we have to know how large the array is so the compiler can allocate it. Even when we dynamically allocate an array using malloc, once it's allocated, it stays a fixed size. It doesn't shrink or grow. So we want now to create a different sort of sequence of items called a list that allows the size to grow or shrink depending on the number of data elements that we want to store. So we can be more efficient and more flexible about memory. So it's dynamically sized. It's also easy to insert or delete an item in the middle of a list, whereas with an array, if you took something out of the middle of the list, you might need to shift things around to plug up that hole. Linked lists are what we're going to use for this. It's not a part of the language. It's not defined as a syntax that's part of the language. So we have to build it out of things that we know already that are in the language. And another important thing to understand about linked lists is that the data elements are not allocated contiguously in memory. So we don't line them up one right next to each other. That has two consequences. Number one, we have to track where the different elements of the array are. So that adds overhead. We have to somehow remember where the next element is. And the other thing is that we cannot compute the location of a particular element of the list like we can with an array. So instead of calculating it, we have to follow the list and use the bookkeeping information that we keep here to find the particular elements of the array, because they can exist anywhere in memory. So let's see how we do this. So the components of a linked list in C is that we need a value for each element of the list. We need some value that allows us to keep data in the list, as well as some overhead, a pointer to the next thing in the list. So the thing that we've covered that allows us to have a value that has multiple parts is a struct. So we allocate a struct, and we have the data part, one or more data fields in that struct, and then we have a pointer field that stores the address of the next element in the array. So here's what that would look like if we do it in C. Each of these things, elements of the list, we call a node. And so we allocate, we define a struct node. We say it's got a data field. We'll just use one field here, but it can, we have some flexibility here. And this data can be of any type. It could be int, it could be float, it could be an array. Anything we want can be the data in our struct. And then we have a field that we usually call next. It doesn't have to be called that, but it is a pointer. It points to the next thing in the list. Each thing in the list is a struct node, so the type of next is a pointer to a struct node. So this is what our typical struct looks like that we use to build linked lists out of. Data field and a pointer field. So this is what our list is going to look like as we create it. Each element will point to the next element, right? And then the last element won't have anything to point to, so we need a special value, null, which is 0, a pointer's value 0, to indicate that we have reached the end of the list. A little more terminology here. As I've already said, each element of the list is called a node. The first element of the list is referred to as the head of the list, and the last element is referred to as the tail of the list. So we can look at this element and know that it's the tail because it has a null pointer in its next field. But the head is not distinguished in any particular way. It looks just like any other list. So we typically we need some other external pointer to tell us here is the head of the list, and that's where we get started. I should also point out that we talk about the empty list as a list that has no elements, and in that case this pointer to the list would be null, right? If there's nothing to point to, then null is a representation of the empty list. So to build our list, we need to create these nodes. How do we do that? First, we allocate memory for a node. Remember, this is dynamic memory allocation, so we're not going to just declare a struct. We have to allocate it in a new place in memory on the heap. And so we use malloc for that. Malloc requires us to tell, well, how much memory do you want? Well, we need enough space to hold one of these structs. So size of struct node tells us how big one of these structs is. Malloc returns that, and we assign that to a pointer that we call new in this case. As I've said when we talked about malloc, it's always a good idea to check the value that got returned by malloc. If there was some error and it couldn't allocate space, that would be null. We're going to skip that in our code just to simplify it a little bit. But you should remember it's always a good idea to check whether new is null after it's returned from malloc. Assuming it's not null, we need to then, number 2, fill in the data field. So whatever we need to do to fill in this field. In a lot of cases, it's just an assignment. If it's an int or a float or something. If it's a string, we would do string copy. Whatever we need to actually put the data that we want into that struct. And then we also want to store something in the next field. Don't assume that it's going to be a meaningful value. It might be garbage because it's just been taken from an arbitrary place in memory. So a good thing to do is to initialize next, and we're going to initialize it to null. If you don't know any better, you should at least initialize it to null so that it's a known value. Okay, so when we create our node, how do we add that to the list? Well, the simplest thing to do to build up our list is to push a new node at the front of the list. There are other ways, and depending on what we want to do, we might want to add the node at a different place in the list, but we'll start with this one. So if we have a list here, H points to this node, and it points to that node and that node. So here's our original list. We want to add a new value to the list. So we have to create a new node here. So in step 1, we do that. Malloc. We assign value. This is going to be a list of integers, for example. So in step 1, we've created this new node. Okay? Now we need to hook it into the rest of the list. Well, if this is going to be at the front of the list, then the node after this will be the old front of the list. So we want this next field to point to this guy, which is the original head of the list. Well, this value here, H, contained a pointer to that, so we can just copy this value into here, and now with new next equals H, now the green arrow and the blue arrow both point to this original head of the list. Okay, now finally we want to change the head of the list because this new node should be the new head of the list, so we replace H with our pointer, H equals new, to point to this new guy, effectively getting rid of that link there. So we've added 2 new links here, we've added a new node, and now from then on, if whoever uses H to point to a list are going to get all 4 of these nodes rather than the 3 that we started with. And then what do we do with the list once we have it? Well, we have this sequence of values. We created it for some reason. Typically, we want to look through it, maybe find something, maybe process the data that's contained in the list. And this process of walking through or visiting each element of the list, just like we've done with arrays, is called traversing the list. So here's a sample function where we've got a list. H points to a list. It gets passed in to us, and we want to add up all of the elements. These are integers, all the elements in this list. So how do we do that? Well, we initialize a sum value to be 0. And now we start with this node. We want to do something with that value, and then we go to the next node and do something with that value and the next node and so on. So we use this next field to get to the next node and walk through the list. I like to create a new pointer for this. You can use H in this case, but I like to create a new pointer so that in case I ever have to remember what the old head was, I can easily do that. So I set P, which is the new variable, it's going to point to this guy. So struct node star P, I declare P as a pointer and initialize it to point to this node. As long as P is not null, I'm going to do something with this list. Okay, so P data tells me the data field of this node, and then I'm done with that, so now I need to point to the next node. Well, I'm done with P, I don't need to point to this node anymore, so I can replace P with a pointer to the next node. P equals P next. So this kind of loop, while P not equal null and P equals P next, is a very typical loop that allows us to walk through the list. And when we get to the end of the list, here P points to this tail of the list, and then when I say P equals P next is null, and so I go to the top of the loop, P is null, and I exit the loop. So this is just an example of walking through a list, and we'll do this many, many times, and you'll see this kind of code over and over and over.